Welcome back to machine learning class. Today we're going to continue to learn the concepts associated with neural network model. In last session, we discussed why neural network algorithm is powerful and also have a quick touch on the feed-forward neural network structure. Today we'll continue from there and also going to cover backpropagation, cost function, and regularization associated with the neural network concepts. First of all, let's quickly review the feed-forward neural network structure. With this kind of neural network, we have input layers which feed in the inputs of features or the independent variables to the hidden layers. And then hidden layers will do some processing, further pass the result, intermediate result to the next layers of hidden layers. Eventually, everything comes to the output layer. As we mentioned early on, if the output layer has only one node, in this case, it's a regression type of problem. And if the output layer has multiple nodes, it's useful for the classification type of problem. And also, let's take one node here as example. On this node, first, it's going to take a linear combination of inputs applied to certain weights, then add the threshold on top. Basically, this linear combination formula get the value of z and the value z plugged into the activation function, and it returns another value based on the activation function. A commonly used activation function is the sigmoid function. So that's the basic setup for the feed-forward neural network. Now let's use one single example to show how the feed-forward network works. So we're using a very simple neural network as example. As you can see, there are only three layers. Input layers, which has two nodes as input. Hidden layer, again, only has two nodes. And ultimately, there's output layer, which only has one node. Now, we already have the neural network loaded with the weights and thresholds. And okay, you can see here, assume those are optimal weights and thresholds that give us the best prediction. So this is our very simple setup of the neural network example. Now, given the setup, given the weights and thresholds of the neural network, we want to make prediction. Now we get certain inputs, input 1 or x1, input 2 or x2. As you can see here, they have values of 3 and 0.5 respectively. With that, how are we going to do the calculation? Remember, we're going to use the linear combination of weights and inputs and then apply to the activation function to generate the value, then pass the value from one layer to the next layer. That's the whole concept of the feed-forward neural network. Now let's do the calculation. The first focus is what's the value after doing all this combination and applying to the activation function. So we know this is the first node, the top node in the hidden layer. It gets inputs from this one here with a weight of 1.6. It also gets an input from this node with a weight of 0.1. Because this one itself has a threshold of 0.5, if we just apply to the formula that we have seen on the early pages, this formula, we should know how to calculate the value of z. And literally, this is what we get as value of z. Threshold first, 0.5, then this input 3 with a weight 1.6, and again, this input with 0.5 and with a weight of 0.1. So this z value itself is 5.35. Now, if we plug this z value into the activation function, which is like sigmoid function in our case, because the z value is pretty big value, 535. With that, it's somewhere probably here. If we read vertically, it's going to get the like corresponding vertical value of 0.9953 because this z value is pretty far off horizontally. As a result, the activation function returns something really close to 1. So this is our first example. Let's also calculate the z value and activation after the z value. And now we'll care about this node, and this node has a threshold of minus 0.04, and it is here. And this node is getting feed of input 3 with a weight 0.4. It also get the feed from this input 0.5 with a weight 0.3. With all this thing together, or with all the inputs and weight threshold together, we derived a z value of 0.95. And again, if we plug into the activation function here, and this gives us something like 0.7211. So this is not done yet, because so far we have only reached the hidden layer and 2 nodes on the hidden layers after all these calculations. Finally, we need to know what's going on, what's going to be output on the output layer. Again, now on this output layer, the threshold is 0.2. Now we are feeding something from this layer as input to here, and we know this value is 0.9953, and the weight is 1.2. Another direction that feeding into here, the final node is from here, the 0.7211, and which has a weight of 0.6. Eventually, put everything together, this linear combination returns 1.827. Again, if we look up on the activation function, putting x as or z as 1.827 somewhere here, and we look up vertically, and this will give us a final value of 0.861. In this case, in this very simple case, if we have certain structure weight threshold like this, and we also plug in the features or the inputs at 3.5, eventually this model will project that the outcome, the prediction by the model is 0.861. So we just walk through the example of feed-forward using certain setup of the neural network and with certain specific inputs to the neural network. Now let's look at another example. Everything is identical to previous page. The only difference here is now we're making the inputs different. Rather than have 3 and 0.05, now we have -3 and 0.5 as inputs. Again, to the same calculation, plugging the threshold, the input, weights from different places, add it all together. We got this negative value, and this negative value, if you look up on the activation function, returns something really, really close to 0, and that's what we get here. Similarly, we do calculation on this layer, on this node, and using the input as this and this, we will get this z value and activation value based on this particular z value, and this gives us 0.19. Further on, we can derive the z value on the final output layer node and also its final prediction. With everything here, we'll eventually get the value of 0.582. So we're just using one particular very simple neural network setup as example, and further on, we provide 2 sets of inputs to this neural network, and correspondingly, we got different prediction values from this particular neural network. All right, so in the previous examples, we are assuming we already know the weight and thresholds on the neural network. Basically, we do not know that until we finish the training of the neural network model. Essentially, the goal of training a neural network model is to derive the optimal weights and thresholds that could yield a minimal prediction error with this neural network. Just like any models, when we talk about training the model, we actually talk about optimization of the model's parameters. In the neural network case, the model's parameters are simply the weights and thresholds, as we have seen in the previous examples. So there's one very efficient algorithm to derive the weights and thresholds, and this algorithm is called the back-forward propagation. So here, let's get a sense how the back propagation works. All right. Initially, we come to this neural network. We do not really know what are the optimal weights or threshold to apply to the neural network because we have a lot of weights on different layers, a lot of thresholds on different nodes and different layers. But what we can do? We just assume random weights, random thresholds. We don't really care whether we get that right or wrong. We just assume any random values for weights and thresholds. Then with that, we apply the feed-forward algorithm, the approach we have discussed, and also I have shown you a couple examples. We're just going to make the prediction on whatever weights and threshold we initially come up with. Once we make the prediction, we can measure how good our predictions are. And we can even measure the cost of the prediction, which is basically a way to measure how good or how bad our predictions are, given the current randomly generated weights and threshold at the beginning. Next step, because when we do the feed forward to the whole network, we got predictions. We can really measure the cost of the prediction errors. And then the next step, step 3, we just need to convert the prediction cost of the errors into certain adjustments of weights and thresholds. Because everything now is just on the last layer of the neural network. We'll first make the adjustment of thresholds and weights for those linking to the nodes to the last layer. You can imagine we're just going to use the gradient descent approach, the one we have come across in the past when we talk about linear regression and logistic regression. Anyway, with that, we first got the adjustment for the weights and threshold on the last layer. Now we're pushing backward. We go from the last layer to the second last layer, then from second last layer to the third last layer, eventually all the way to the very beginning. So in the rippling way, in the backward way, we're adjusting the thresholds and the weights layer by layer in a backward fashion. Now, all the weights and thresholds, aka all the parameters on the neural network, got adjusted based on the last rounds of prediction error. So with that, we can repeat this process 2, 3, 4, 5 again. Every time as we go further, the prediction error is going down and getting smaller, or the cost is getting smaller. We'll stop until we get a point that we are satisfied with the results from the model's prediction. Then we call an end. By that time, after so many rounds of so many iterations of the adjustments of the parameters, again, weights and thresholds, this neural network is going to predict very, very good outcomes, and we're happy with that. And then we call the end to the training process. Essentially, you can see overall the approach is still the gradient descent approach as we have seen in the past. That's how we adjust the parameters gradually. And another important concept here is Since the neural network is not just one simple layers of parameters, basically there's many layers, probably multiple hidden layers in addition to the output layer and input layer. So we really need to adjust the many layers of parameters. The way we're doing that is we're leveraging the derivative, the chain rule. We're going backward one layer to the earlier layer, starting all the from the very last layer, the output layer. We're not going into depth of how the derivative, partial derivative works, how the chain rule works. But overall, you just remember the approach again is overallly a gradient descent approach, and we're leveraging the derivative, the chain rule, to make this process very efficiently by going backward. So that's the name of backward, back propagation, where it's coming from. Well, we talked about, we're going to, on previous page, we talked about we're going to adjust the parameters based on the cost, right? Then what's the cost function we're going to use? Well, here is the one we have seen in the past. If it's a regression problem, typically a common cost function is certain um, like sum squared error, just like this. Um, so we have n observations in the training data sample, and for all of those, we know what is um, actual value yi prime and what's the model projection error value, and we can take the difference of those two and square them, and we sum up all the residuals, all the errors across all the n examples and samples in the training data, and sum them up, then divide by n, so that the number won't be too big. We basically literally we take the average of the sum of square errors. So that's for the regression. Uh, And in another possibility is we're dealing with classification, right? Again, the classification could be the binary classification or the multi-class classification. No matter what, we're going to use the cross entropy function as a cost function. If you still recall, we covered this binary. In this case, we talk about the binary classification, means the outcome either 1 or 0, either this or that, either true or false. So in this binary classification case, if you remember, we talked about this cost function in our logistic uh, regression section. And this is just literally the formula we're going to use. And here again, we have n observations in the data. And for each particular ith observation, this is the actual categorization, either 0 or 1, and correspondingly what is a model's prediction and in terms of probability, some a value between 1 and 0. So this is a binary classification for which the outcome is either 1 or 0, either this or that. To generalize the binary classification cross entropy function to multi-class classification, here is what we get here. Similarly, the structure actually has a very high level of similarity. Again, we're dealing with n observations, and because now we potentially there's m classes, there are n possibilities, right? So for each actual y, it must be falling into one of the m categories or the m classes, because we're just dealing with the problem that is the observation can only fall into one class, not 2 or 3 classes at the same time. As you can imagine, if that case, if we do the extend the formula, expand it, eventually for anything other than the true category, this term will be zero. So they just like will disappear. And what's only left is for this when the actual observation fall into certain true category, for which case you'll get one, and then the whatever the model's prediction will plug in and give the costs. Again, we sum them up, we divide by n to calculate the average. So that's the multi-class classification cross entropy and cost function. How to make sense out of it? Here, let's just get some intuition around the multi-class cross entropy cost function. Again, this is the original formula. Now, in order to understand it, let's take a very simple example. Now, let's assume we only have one observation. To simplify this cost function, and also in our particular case, we have m equal to 3 means we only have 3 potential classes for which the outcome can follow into. With that, this cost function is simplified into this form from here. And furthermore, let's take one example. And for this particular observation, its actually classification is a second class. So the first class will have y value equal to 0 because it's not the first class. And the third class, its y value, actual value is also 0 because it's not third class. It's the second class. The y value for the second class is 1. Now let's see, we have a model. Given everything we have talked about, this model makes a prediction that is the probability of falling to the first class P1 is tiny, 0.01, and probability falling to second category is pretty big, 0.998. Then the probability falling to the third class is also very tiny. Now let's plug everything, all those inputs, p values, y values into this formula. This is literally what we get. And this gives us cost of very tiny value, 0.002. Looks pretty good. And because the prediction line up with the actual very well, and that's as a result, the cost from here is very small. Now let's see, we're still with the same observation, but now another model makes a prediction which puts a lot of weight, a lot of probability into the first category, like 0.998, while making the second category probability really, really low, and the third category also low. With that, the overall cost will become this guy, 6908. See, this one is much bigger than this one because we can tell the first guy is a good prediction, and with that, the cost is really low. And the second guy is bad prediction. With that, the cost is really high. That really achieve our purpose using such kind of cross entropy cost function. You may also get the idea again, right? In the end, even though we have summation across different class, in the end, what matters is really the component, the item for which where the actual value for the observation is, right? Because everything else, the corresponding y value will be 0, all the items will be zeroed out, only one term left. Then for that one term, if model prediction is close to the actual, also give something really too close to 1, you get a very small prediction error. Otherwise, the prediction error will be big and the cost will be big, and that's why we punish it. All right. So we're going to talk about now the last topic. So we talk about the back propagation, and we talk about the purpose of back propagation, and we'll also talk about just on last page what kind of cost function we're going to use for the neural network back propagation to adjust the parameters. One thing we should call out is for any model, not just neural network model in particular, but especially for neural network model, it should be careful. We do not want to overfit the model. What overfit means is we actually, if we do not put any constraints, we may end up with a very, very big neural network. And there are so many parameters in this neural network relative to data size. As a result, the model can be a perfect fit the training data because kind of so many parameters, you have so much freedom, you can make things just singly matching the training data perfectly. But once you go beyond the training data, you put a new piece of testing data into it, the model may not predict well. Such kind of problem is called overfitting. How to prevent overfitting? One thing people commonly do is add additional penalty term to punish having too many weights or too many parameters for the neural network, and this is a typical way to do it. Basically, we do the summation of a square of weights and then essentially apply certain coefficient lambda and make the additional penalty term of the overall cost function. Again, if this is regression, it kind of like some squared error type of cost function. If this classification, this will be cross entropy type of cost function. Anyway, we'll have additional penalty here to punish of having too many parameters. Eventually, if you have too many parameters, this part will become very big, but this part, pure cost will be small. But the overall cost is really a balance between the prediction cost versus the penalty of having too many parameters. So you may notice that we have 3 sigmas here. So why is that? Because the weights, in order to make the weights very clear in the neural network structure, we actually need to have 3 alphabets to annulate where those nodes weights are for, right? For which nodes and where it's coming, where it's going. And there's certain little bit more formal notation around this, just something like this, and actually have those in the appendix, not just for the weight and also for the threshold and for the value after the activation. Anyway, just let you know, because in order to make the weights really clear, like to find out where it's coming from, where it's going, and we really need to have 3 letters, and that's why when we do the summation of weights, we need to have 3 sigmas, because each letter itself is also a variable. Start with first to the last. The last could be the last layer or the last nodes in the layer, something like that. Anyway, that's all for today's class. Basically, today's class is a follow-up on the conceptual discussion associated with neural network.